All right, let's talk about one of the most famous, most profound, and honestly, most mind-bending experiments in the history of science. This is the one that completely rewrites the rules of reality as we know it. So, yeah, let's just dive right in. So, to get started, let's just think about a really simple setup. Imagine you have a wall with two little slits in it, and you're firing something like a tiny marble or a pellet straight at it. The pellet is going to go through either the left slit or the right slit, right? So where do you expect it to end up on a screen behind that wall? I mean, common sense tells us you'd get two simple lines of hits, one perfectly lined up with each slit. Makes sense. But that's not what happens. Not even close. Instead of two neat lines, what we actually see is this complex striped pattern of many bright and dark bands. And that is the core mystery we're going to unravel today. Why does reality not care about our common sense? To figure this out, we've got to break down the experiment itself. So first up, let's look at the basic setup. It's a really simple design, which is what makes it so brilliant. First, you've got your source, in this case, an electron gun that can fire single electrons. Then you have your barrier, just a simple wall with two very thin parallel slits cut into it. And last, you've got a screen that acts as a detector. It lights up wherever an electron smacks into it. That's the whole shebang. Source, barrier, screen. You know, this idea has been around for a while. Way back in 1801, a guy named Thomas Young did this with light, and he proved that light acts like a wave. But things got really, really weird in the early 20th century when scientists decided to try it with electrons, actual physical particles. What they found, well, it became the foundation for all of quantum mechanics. Okay, so let's get back to that strange striped pattern. What in the world is it telling us? Because this is really our first big clue. So that pattern of many stripes, it's not just some random thing. Physicists saw this and they knew exactly what it was. It is the textbook signature of waves interfering with each other. So think about tossing two stones into a still pond. The ripples spread out, right? And when they meet, a couple of things can happen. Where two wave crests meet, they add up to make an even bigger wave. That's our bright band. But where a crest meets a trough, they cancel each other out completely. That gives us a dark band. It's called interference, and it's what waves do. And this is where it gets confusing. The pattern is screaming wave, but we know what we're shooting. We're shooting electrons, tiny solid particles. They're not waves. So how is it possible for a single particle to create a pattern that looks like it was made by waves that are overlapping and canceling each other out? To try and solve this, scientists got really clever. They thought, okay, maybe the electrons are just bumping into each other on their way to the screen, creating this pattern. So they designed a way to rule that out.
The idea was pure genius. They slowed the electron gun way, way down, so far down that it would fire only one single electron at a time. They'd fire one, wait for it to hit the screen, and then fire the next one. This way, there's absolutely no way the electrons could be interacting with each other. Each one is on a solo mission. Surely this would solve the puzzle.
And at first, it seems like, yes, we're back in the land of common sense. Each electron travels from the gun and hits the detector screen as a single, tiny point of light, a distinct dot, exactly what a particle should do. Phew. But here's the kicker. They let the experiment run. They let thousands and thousands of these individual dots build up on the screen, one after another after another. And as this picture slowly begins to take shape, the impossible happens all over again. The wave pattern comes back. Dot by single dot, it rebuilds itself. Even though each electron traveled completely alone, it somehow knew exactly where it needed to land to help build this larger wave pattern. It's as if each particle went through both slits at once and interfered with itself. So think about what this means. The electron leaves the gun as a particle. On its journey, it seems to behave like a wave, exploring every possible path, including going through both slits at once. But when it hits the screen, bam, it's a particle again, landing in one single definite spot. It's somehow both at the same time. Now, this is already completely bizarre, but the rabbit hole goes deeper. There is one final twist to this story, and I promise you it is the strangest part of all. Scientists decided, okay, we're going to try to catch this electron in the act. We're going to watch it. So what they did was place a tiny little detector right at the slits themselves. Think of it like a little security camera whose only job is to see which path the electron took. Did it go through the left slit
Or did it go through the right one? A simple question. And what they found is, honestly, it's just jaw-dropping. The very moment you turn on that detector to see which slit the electron goes through, the interference pattern vanishes. It's just gone. And what's left in its place? Two simple bands. Exactly what our common sense expected from the very beginning. The very act of looking at it forces the electron to act like a normal particle.
Just let that sink in for a second. When we're not looking, the electron is a wave of possibilities. It could be anywhere. But the moment we measure it, the moment we observe its path, that whole wave of possibilities collapses, and it's forced to pick one and behave like a simple little bullet.
So, what does this all mean? Well, it means that down at the quantum level, the universe just plays by a totally different set of rules. It's a whole new kind of reality.
And here are the new rules of the game. First, things can be both particles and waves at the same time. It's called wave-particle duality. Second, before you measure it, a particle exists in a state of all possible outcomes at once. This is superposition, like going through both slits at the same time. Third, the simple act of looking, of measuring, forces nature to pick one single outcome. And finally, because of all of this, we can never know for certain where one electron will go. We can only talk about the probability of where it might land.
And believe me, this isn't just some abstract philosophical puzzle. These weird quantum rules are the bedrock of our modern technological world. Without understanding this stuff, we would have no quantum computing, no electron microscopes, no semiconductor physics, which means no smartphones. This bizarre reality is literally the engine of our modern lives. And that brings us to the final, really unsettling thought. This experiment proves that the universe behaves differently when we measure it, when we look at it. So it forces us to ask a question that physics might not ever be able to answer. What is reality actually like when no one is watching?